Okay, so let me start out. Oh, guess what? Last homework. So this is it. Due finals week. Hopefully y'all can get kind of caught up on the homework by then. If you struggle with that, just let me know. The first couple of days of finals week, I've got to babysit my daughter, but I will have my usual office hours. I might have to Zoom them, right? But I'll be available for finals week, pretty easy. So, and we'll have a get together on Thursday during finals time. We'll maybe have like the last lecture. It is at 11:30 on Thursday. I think it's our final exam time. Since it's near lunch, I fully expect somebody all off last time to bridge my height and have a piece of the class. So we'll see if we can capture that on YouTube or something. Let V, so that this last one we said, let V be a domain. Show the following are equivalent. V is a quasi-local Bayesian domain. Now you probably know what one of those words are. Quasi-local means there's a unique maximal ideal. Bayesian, what does that mean? How many of you remember what a principal ideal domain is? A Bayesian domain is sort of not necessarily the theory and analog of this. What it means is some ideals might not be finitely generated, but every ideal that is finitely generated must be principal. Right? So if you have an ideal that has a property that every finitely generated ideal is principal and it's got only one maximal ideal, it's the same thing as valuation domain, which I haven't told you what it is yet. The valuation domain is a domain if you take any two non-zero elements, one of them has to drive the other. That seems a pretty strong condition, doesn't it? And it is. Let R, number two, let R be a domain with a quotient field K. Now, last time, Grant told you about what it means for an element to be integral. It's the root of some monic polynomial with coefficients. Here's another definition. An element X in the quotient field of R is said to be almost integral if there's a non-zero R that I like to call the anchor, such that R times X to the n is in R for every X in n. So R is an element of the base field, and R is so strong that it sucks in all powers of X, no matter how big. And we say, on the other hand, that a domain is completely integrally closed if it already contains all of its elements that are almost integral. Now, let me point out that this definition here was confused historically with integrality. I mean, it looks like it might be related, but you know, what's it got to do with that? So, number one, I want you to give an example of an element that is almost integral over R, but not integral. And actually, some of the next few problems will give you kind of a hint where to search for that. As I said, historically, when it sort of early on in studying integral elements, it was thought that this definition was equivalent to integrality. It's not. Number B, show that if X is an element of the quotient field that's integral over R, then X is almost integral over R. In other words, prove that our terminology isn't stupid, right? Because you would think that anything that is integral must be almost integral, right? Otherwise, it's not very good terminology, is it? Right? So anything that's integral actually, so if you have an integral element, as Grant told you, then there'll be some R that satisfies this. Show that if R is an Noetherian, then any almost integral element is integral. So if you have a ring that's an Noetherian, that is, all the ideals are finitely generated, these two notions are exactly the same. This gives you a hint for part A, because when you're sniffing around to find something that is almost integral but not integral, you better be looking at a ring that's not Noetherian. Otherwise, it's hopeless. And finally, let V be a valuation domain that is not a field. This is just, this is actually true otherwise. Show that V is completely integrally closed if and only if V is one-dimensional. And what one-dimensional means is every non-zero prime ideal is the maximum. Right. So this should be like a kind of a fun set. Let me know if you get any trouble with it. Any questions on that? Okay. So let's talk about some of those words then. So the first thing I want to do is talk about right. Let me start with a valuation domain. Now, what I told you when we were talking about the problem set is valuation domain is an integral domain where you're taking two non-zero elements, A and B, either A divided B or B divided A, right? That seems like a pretty strong thing to say, right? Can anybody think of a class of fields that are automatically valuation domains? If I take any pair of non-zero elements, one of them divides the other. Think simple and you won't get too far in the field. My delicious puns aren't going to keep it there. So how about a field, right? What happens if you take two non-zero elements? They're both invertible, right? So they clearly, in fact, if you have a field, if you take two non-zero elements, they both divide each other, right? So evaluation domain is sort of like half a field in that respect. You're only guaranteed that one of them divides the other. Still, this seems like a pretty strong condition, right? Seems like evaluation domains are almost fields. Can you think of an example of a valuation domain that isn't a field, right? Whenever you make a definition, that is always important in mathematics. Make sure that it's not vacuous, right? I mean, do we actually have a non-trivial sort of example of this? So let me start off with what I'm going to call valuation. We'll kind of tie it together. Let K be a field. A valuation on K V on K is a function V from K. When I say K star, what I mean are the non-zero elements of K. So K star, I'm really thinking of as a multiplicative group here to gamma, where gamma is a totally ordered abelian group. Okay, so evaluation is some function from the non-zero elements of K into some totally ordered abelian group. And I want to satisfy a couple of things. Number one, I want so basically, this one says it functions like a logarithm, right? It's a homomorphism from the multiplicative part of K into the valuation of AB, or the value, I should say, of AB is the value of A equals AB. This basically functions like a logarithm, and it's a homomorphism from the multiplicative group of the non-zero elements of the field into whatever this totally ordered abelian group is. And two, I want to deal with addition here. Well, actually, let me put the caveat. I want this to be defined. The value of A plus B is greater than or equal to the minimum of value of A and equality holds quality holes values are different. Okay. And of course, so let me also say, I put in the caveat of A plus B is not zero. And of course, A and B are assumed to be not zero since I can make value of them. Then this is greater than or equal to, and then those two quality holes, their values are different. Okay. So let me go ahead and actually check into this. So this is what we call a valuation. This is what this function is. And in a certain sense, it measures size. It's sort of an attempt to measure the size of elements in K. Why is it measuring size? Because this is a totally ordered abelian group, right? So given any A and B, right, you take the value of A and the value of B, these values are actually in a totally ordered abelian group. So you can compare them, right? Either the value of A is bigger than the value of B, value of B is bigger than the value of A, right? Or equal to. And in fact, a good totally ordered abelian group to keep in mind is the ordinary integers, right? They're in an active for any totally ordered abelian group, you can define a valuation domain that takes these values. Some other ones that you might consider the rational numbers, the real numbers, etc. Let me give you the following proposition. Let V be an integral domain with quotient field K. With quotient field following conditions are following. Number one, for all A, B, and B, technically this even works for A and B, for example. Given any two elements of your domain, one of them divides the other. Two, if omega is in K, which is the quotient field, then either omega, if omega inverse is in B. That is, take an element of the quotient field, any element you like. It's either already in B, or it's reciprocal to B. And three, B is equal to the set of X and K such that Bx is greater than or equal to 0, union 0 for some valuation B on K. Any domain satisfying one, hence all of the above is called a valuation. Okay. So these are all equivalent. Let's look at some examples. Any field is valuation domain. Because if I take any two elements of the field, one of them divides the other, right? Notice this is certainly satisfied by field because the field itself is K, so anyone making a case there already. No worries, right? And in fact, its inverse is in there as well, unless omega happens to 0 in the first place. By the way, what's the valuation? Okay. Right. So suppose that anybody name valuation. So these conditions here are equivalent. What's the valuation is here? Well, how about it? It's actually sillier, right? So the key is what's my value group here, right? What's the totally worth billion group? It's 0, right? Let's check if this works, right? Let's see, shall we? So just take every non-zero element field, let its value be 0. Is this a value? Is this valuation? Well, it certainly is a function into a totally ordered billion group, right? Because the trivial group is certainly totally ordered. The value of AB is still 0, which is 0 plus 0, no problem there. And if A plus B is 0, then the value of the element field is, well, this is 0 is greater than or equal to the minimum 0, 0, so this works, right? Now let's check this out. V is a set of X and K such that V of X is greater than or equal to 0. That's everything that's non-zero. Then you throw in 0 and you got it. Right? So actually, for the field case, it's the most trivial things. The value group is just contributed to it. But so in fact, this is a universal thing, right? So if you have any field, then its value is just a function in the trivial. How about something a little more to it? How about evaluation? So my takeaway from that previous example is, fields are silly in the sense that given any two elements, one of them divides the other. And what did I get from my silliness? I got a trivial group, right? For the values. How about an example of evaluation domain that's not good? So we have to have a non-trivial value. Anybody think of them? So I'm looking for an example of an integral domain where if I had any two non-zero elements, you think hard about it. The power is at your fingertips. What's that name? The problem is, if I understand your template, that's not a domain.
Oh.
I need an integral domain. but the ring of power series. This is actually valuation. Let me prove this to you. So suppose I have a non-zero power series. Right? Well, this power series is sort of like, you probably don't know it well, but let me write it this way. Now, notice that I assume that my power series is not the zero series. And so that means it must have at least one coefficient that is not zero. I will let AN be the smallest such coefficient that's not zero. What are you just dying to do when you see the series here? I mean, if you think about factoring or something like that, correct? Now, what can you say about money? Well, it's very important that this power series and coefficients stay together. What can you say about that series AN? Since it begins with a non-zero element, or since its constant term is not zero, what can you say about that? You all remember this? Y'all remember that? If you have a power series over a field, if the first term is not zero, then it's a unit. Everybody recall that? You'll recall it? Well, let's go through that. But it's important that we know that, otherwise I'm just blowing smoke here. So let's prove that. The first observation that I'm going to make, I'm not going to do a hardcore proof because it actually requires some steps. Suppose I have power series. Actually, whether or not I'm over the field, I claim the series is always a unit. Okay, now I'm going to be super sloppy about this, but maybe you all get me. Let me construct its inverse. All right. Let's see if we need to insert. All right, if I want to build the inverse of this, first term should be 1. But now I've got some equations. 1x squared. Now, the real question here is, can I solve these equations, right? Because what equations do I have? Well, first of all, I match on the constant term, right? I've got a 1 there for sure. And then I have to satisfy the following. Correct? Because that has to be 0. Right? But I can solve this. This is doable because I get B1 is minus A1. So now figured out what B1 is. Agree? Just let that be minus A1 and I'll be right up to the linear term. Well, now I've got another equation. For the x squared term, I get B2 plus A1 B1 plus A2 is equal to 0. I think. Right? But I know B1, and so B2, well, actually, it should be minus A1 B1 minus A2, which in this case is A1 squared minus A2. So I know B2. Agree? Now I've got to determine B3. Well, B3 times 1, so I've got B2 A1 plus B1 A2 plus A3 is equal to 0. But again, B3 is just this. And I already know from the previous steps B2 and A1, so now I'll solve B3. This keeps continuing like this, and so I can solve for every BI. Another way to see this, let me illustrate this yet another way. The important thing here actually is this one here. The next term I'll have B4. B4 times this is this, and everything else is determined. Another way to see this, like I said, is this. I should do this anyway. 1. So imagine dividing only from the other end. 1 plus A1x plus A2x squared plus A3x2 plus A4x4 and subtract. Like that. Now, how many times does 1 go into A1x? Well, minus A1x times minus A1 squared minus A1 A2 x cubed minus A1 A3 x4. You subtract again. This. And now how many times does 1 go in here? That. This process continues because of the fact 1 will divide into whatever the leading thing that comes out of here is. And because this is power series, you never have to stop, right? And so this is kind of another way that illustrates the same concept. So the upshot is this. So if you have a power series and the constant term is 1, and the power series is green. If I agree with that? Let me up the voltage just a little bit. Yeah. In fact, it really didn't matter. The first one was 1. The only thing that really mattered was it was a unit. And if you don't believe me, just multiply this by the unit U, and it translates to unit. So this is kind of a celebrated theorem that in the ring of formal power series, a power series is a unit if and only if its constant term is unit, right? So that one you didn't see last semester. Well, now you know. And this is very different than polynomials, right? Because, for example, this polynomial in Rx is not a unit, right? Because it's of degree 1. What are you ever going to multiply a degree 1 polynomial by and get you degree 0? It's impossible, right? However, power series range turns into a unit. Okay, so any questions? So let's get back to the lecture at hand. Start with say. And this series right here has AN is not 0. And when you're over a field, if this is non-zero, it's a unit. Right? So here is the important thing that I've gotten out of this. If you have a power series that is not 0, then it is some power of x times a unit. And of course, that power of x could also be the 0 power. Everybody okay with that? Just pull out x until you get out the leading coefficients on 0, and the rest is a unit. So if F and G are in R power x or F power x, I'm going to write that. So suppose I had 2 non-zero power series, then f of x is x to the n u1 u, and g of x equals x to the n b with n m, and the natural number is u0 and u b units. and one of these has to divide the other. Can anybody tell? How could I tell by looking at F and G which one divides the other?
The smaller X.
That is correct. That's all I got to do is look for the one with the smaller power of X. So, the divisor, that is the one that divides the other one, is one with X and then. Yeah. And of course, if it's a tie, then they both divide each other. So let's take apart this valuation thing here. Notice that the value of AB, I can rewrite this as X to the N plus M times UB. And since U and V are both units, this is still a unit. This is M plus M, which is the value of X to the N U plus value of X to the M. Right. Now let's suppose also that when I add these up, I don't get 0. Without loss of generality, let's say that M is less than or equal to N. Okay. If I look at X to the MV plus X to the NU, when I add these up, this is X to the M times V plus X to the N minus M U. Everybody okay? And of course, this is not 0 by assumption, because I assumed when I added them up, it's not 0. So the value of X to the M U, or V that is, plus X to the N U is equal to the value of X to the M. It's the value of the southern S. And V is very poor choice. I'm sorry about that. Plus. Which is greater than or equal to, which is mean value A value. Right? Because I can pull out an M here, leaving me with this mess right here. And so the value is at least the value of the one that I can pull out, which is the minimum. Do I agree with that? And notice there was also a statement in there. Notice that if N is greater than M, then what happens is this. So here's what happens. If N is greater than M, then this is a unit plus a power series that has some number of factors of X in it. So this is actually valued 0, right? And so you get equality. If N equals M, then you have B plus U. So maybe not. Because what you're down to here is V plus U. If you have equal powers here and that cancels, V plus U might be a unit, in which case you get equality, or it might not, right? So for example, you might have, when you add a 2 unit power series, and let me just give you a short power series. This one's still a unit, right? This unit plus this unit is still a unit because constant term times 0. But when you add these up, you get x plus x squared, which is not a unit. Right? So the outcome of this when n equals n depends on what u and v are, as a matter of fact. Okay. Any questions on that? How about the valuation method in this example? So every element of F power max is either 0 or a form x to the n u, or n is greater than 0 and u is a unit. And of course, a unit just means a power series with a non-zero constant, right? What are the elements of the quotient field? We'll call the quotient field K, like in our notation here. Is there are fractions? I'm going to leave 0 out of it. So consists of 0 and fractions in the form x to the n u1 over x to the m u2. Right. That's what the quotient field has. And I can simplify this. Notice this is still, this piece right here is still an F power X. Because U is a unit in F power X, and U2 is a unit in F power X, so it's inverses in F power X. So this is just a power series in F power X that starts with a non-zero constant term. And this is a power of X multiplying it that can be either positive or negative. Right? Because it might be the case that n is bigger than n. So, anybody want to guess what our, so we have B from K star, and again, anybody want to guess what our totally ordered Vivian group here is? It is Z. This is basically, this thing is what is measuring the value or the size. Z is a totally ordered Billion group. And here's the way this works. Notice that this consists of the non-zero elements. So if I have X, the K, U, because remember, any element of the quotient field is X to some integer power times the unit, and F power X goes to K. And of course, K can be positive or negative here. Okay, any questions on this? Questions? Let me give you a note. By the way, Yeah, I think Sandy's reports. We'll start. Here's another reason. Actually, I'm looking to be more precise. Of course, Z itself is not a valuation domain because take 2 and 3, either 2 divides 3 or it's 3 divides 2. Right? There are infinitely many valuation domains. You can see rational numbers. Go ahead and name one of them. They're actually indexed by the primes. If you take any non-zero prime ideal and localize, you get a valuation domain. It's actually very similar to the power series. Let me recall for you. Z localized P. This is the rather unfortunate notation. Z localized this prime ideal doesn't mean that I'm taking fractions or the denominator out of the prime ideal, because in fact, when the denominator is 0, right? It means I take the fractions denominator not in this. So this is these are fractions A over S, where S is not typically type, or this is actually valuation domain 2. And to prove that this is valuation domain looks almost exactly like the power station. Because what does a typical element of this look like? Well, let A over S1 B over S2 be Z localized P. Let me point out that there are a lot of units in this ring in the following sense. In fact, can somebody characterize what does it mean? I already know that S is relatively prime to P, right? No factor P there. What does it take for this animal to be a unit? Well, let me be sloppy. To be a unit, you've got to invert a fraction. That is correct. This is a unit if and only if the numerator is also relative. Right? So I can sort of measure size in the following way. So if A over S is not 0, then A over S can be written as A e to the n S with GCD A prime B 1. The idea is you take A and you jerk out all the factors of P that you possibly can. Maybe there's enough in there. And of course, N might be 0. Everybody agree with that? And your value is basically measuring how many factors of. So the role of X was sort of value measure in the power series. P plays the same role here. So if A over S is not 0, then A over S can be written as P to the n times a unit, because A prime over S is the unit. And so the quotient field Q in Q, any non-zero element can be written as P n U, or P to the S1 over S2, where GCD S1 GCD PS2 1. And M is in Z. So in the same sense, a very similar way, you get the value group Z here. For this particular one, here's the way this one works. And we'll talk more about this next time. How many of you have ever heard of p-adic integers? You ever heard of that? Well, they come from this. So write your element as P and N, S1 over S2, like in this form here, where N is, and this goes to, this is what is called p-adic valuation. There's one for every prime. How many of you know what the real numbers are? You complete the ordinary rationals under the notion of absolute value. You can complete the ordinary rationals under each of these p-adic calculations and get what's called the p-adic rational numbers, as a matter of fact. So these are actually very important in number theory and some forms of analysis. Okay, any questions? We will carry on next time. You all have a good one.